All right, I was waiting on Josh and he must be having network difficulties. So I guess I will do the lab for him. So I will turn on my screen sharing and put that together. Let me get to your lab because this is not yours. So to get today's lab, you would go through Blackboard, and I bet it's not even here yet. Yep, there is no lab 28. Okay, we'll get to it a different way. We'll get this fixed, but I can't do two things at once. Hard to believe, I know. So if you go to this URL, I'll put it in the chat box. Click on the teaching, pull down accordion dealy bopper, choose ENGR-1330. It will take you to this page and go to the instructor notes. Scroll down to about lesson 28, which is today's activity. Laboratory 28. You click on laboratory 28, that brings you into the lab. If we click on exercise 28, that brings you into the exercise. If you want to get the notebook, you would right click and save it this way. So that'll get you the lab. So if you right click and download that to your machine, then you can start your Jupyter Lab instance and work on the lab. So I'm just going to go straight to, actually, no, I don't want to do that because I'll break it. I'll go to my copy of the server. Labs. Let me go ahead and work on a copy. Okay, so we will work on a lab called copy. What's that? All right, so our goal today is to learn how to assess fitness of a regression model and compute and plot prediction interval. So by background, back in lab 26, we examined regression using both primitive Python and some packages. And now we're going to put those ideas into practice. Since we're referring back to lab 26, it just might be worth our trouble to have a copy of it handy. So let's go get that lab. Okay, it's that one. What we want to have handy is down here near the bottom where we have the different packages using stats model, and the other package was sklearn. Okay, so we'll leave that one handy, but we will work on this. So we have a polymeric material that has a solvent, and we have solvent concentration in weight percent in time in seconds as it does its polymerization thing. We've been instructed to fit a linear model to the data, plot the data and the models, presumably on the same plot, and then determine the equation of the model and the corresponding root mean square error and R squared value. So let's do those one at a time. The first and most obvious thing to do is to load in the packages. So these are my guess of the ones that we'll be needing. So I will load those and run it. And there I have a 1 there. It's been successfully prototyped. Next, we need to make a data frame. So we'll have a concentration and time, which is taken from this. If you decide to do it by cutting and pasting, there's a little bit of editing involved. I just typed it in. And we will put that data frame, we'll put these two lists into a data frame using the pandas data frame function. We're going to name the list associated with the list time as time, and a list associated with the name concentration as CONC, conch. And then we'll check to be sure that we built the data frame correctly, or as we anticipate it to look like. Sure enough, we do. We have time in one series, concentration in another series. We have 0, 55.5, which corresponds to the first one. And like the fourth one is 38 and 4. So 38 and 4. It looks like we have built it correctly. We are happy campers at this point. Now we want to go ahead and make sure I'm doing it, fit a model to the data. So I'm going to choose to use the model in the stats model formula API as SMRF, so SMF. And from that API, I'm going to choose the ordinary least squares modeling tool. And I'm going to construct the model that I want to determine a model that relates concentration to time, where concentration is the predicted value and time is the predictor. And our data are going to be contained in a data frame named polymer, which is the data frame that we built up here. And we will perform that transformation and we'll put it into an object called a model. And then we will operate the fit utility or the fit method in model. And we can extract the intercept and the slope using these commands here. We can extract r squared from the model object as r squared, and we can get the root mean square error by taking the total mean square error and computing its square root using the math package. So a lot going on there, but just a few lines of scripting is all that's required. And we're done. Nothing much to see here. To find the various values that are available to us in the ordinary least squares tool, we could go visit this location, and this is the API reference. So we choose from stats model API ordinary least squares, and then in ordinary least squares, it has some examples. And from the examples, we're able to construct our model. This thing up here is bothering me. That's less of a bother. Okay, so now we have in the model object, we have fit our data to a linear model. So we have a model that says concentration is equal to some constant plus some other constant multiplied by the value of time. Now we will go ahead and make predictions. So we're going to create a new model called NP-Pred. The name is just something that was fun. We could call it polymer prediction. That might even be smarter. Polymer Pred. And we'll run from our model object, we'll use the predict. How does it do that? We will use the predict method and it will produce a predicted value from the red line for each of our input data points. Now we're going to build a title, and here's where we're doing a whole lot of stuff. So we're going to have a title. The name of this plot will be called concentration history. We're going to build a string that says y equals the value of the intercept plus the value of the slope times x. The r squared value is equal to r square that we pulled out of the model object, and root mean square is the root mean square that we pulled out of the model object. Then we'll create our figure. We'll make a plot based on polymer time and concentration, a plot based on polymer time and polymer pred, P-O-L-Y-M-E-R, pred, and we'll set the line width on that for 2. We will leave the original data without a line width, so it'll just plot as markers. The marker we're going to use for that is a dot, and the polymer pred, we're choosing to plot it in the color red. Our plot label is time in seconds. Our Y label is solvent concentration in weight %. Then we'll plot our title. And we probably should also plot a legend. So let's do that. So legend is expecting in this case, a pair of strings. So the first one we want to give it is observed. There's our legend, and finally we'll show the plot. So let's run all that. And I broke it because I one too many vowels. And there is our result. So there's our straight line going down through our polymerization data. We're having it return the actual value. So the red line is y equals 51.6 minus 2.61x. The r squared of the fit is 0.985, and visually looking at it, I guess that's arguably a good fit. If a straight line is the tool we're going to use, then that's a pretty good fit. And our root mean squared error is 17.41. And without understanding the scale, that is not terribly useful in this instance. If we examine the dots, a straight line worked okay here, but it may not be the best possible because it looks like there's curvature here and then kind of an inflection point, and then it curves down again, and then another inflection point. It's almost as if this is happening in 3 stages. But given that our only tool right now are straight lines, we'll have to go with it. Now suppose we were interested in trying to get an idea of the uncertainty involved in any prediction that we make from this red line. We can use the ideas from the lesson and build a few additional plotting calls to generate upper and lower prediction intervals and upper and lower confidence intervals on the model parameters, essentially where the red line is likely to fall. To find that, we would go visit this part of the documentation and reading through here to learn how to extract the things that we're asking for. And then the various model classes, results classes. And each of these usually has some kind of example, except the one I clicked on just now. So that was how I learned how to make stats models, sandbox, regression, prediction interval stuff. And we go ahead and make the plot, and there's our plot. Okay, so the red line is what? Let me get the chat up for those of you that are too shy to talk. Red line is model line, good. The blue dots are observations, yeah, good. The orange dashed envelope line is a confidence region for what things? Bit of a trick question probably, but make a guess, 50-50 chance of being right. Okay, those are not bad guesses. The orange range is the confidence interval for the model parameters. So it is what would happen if we changed the slopes to all the possible slopes that were in the table and change the intercept to all the possible intercepts. And if we just kept doing that and drawing a line over and over again, it would completely fill in between the orange area, and that would have a 5% error rate. The green ones are the upper and lower prediction values. So the prediction uncertainty is always bigger than the model uncertainty. In this case, they look almost parallel to the model line, as they should. So if we were to make a prediction at this point, our best guess is what the model tells us, is somewhere right here. But the actual value of what we're predicting might be as far down as here, or might be as far up as here, with a 5% chance of error. It's a 5% chance that actually falls outside the green line. Okay, our first exercise. Let's fix the plot to include a title, X and Y axis labels, and a legend. So who wants to tell me what to do first? Let's do the title first. How do we get a title into this sucker? Well, while you're pondering that awkward science, go up to the first graph and copy the code. Perfect answer, because that's exactly what I'm going to do. So we'll go up to the first graph and copy the code. Except I guess I should copy the right one. I need the title line, and we'll go ahead and get the title line built. And now we'll save some time. We kind of want to do the titles and that stuff at the end of building things. And there's a reason for that. And I'll do it wrong in a second so that you can see what happens. I guess we can build the title line right before we need it. Okay, column concentration history, and hopefully we didn't lose anything with that. Let's go ahead and run that and see what happens. Okay, so now we have our title, kind of like the same one as before. Next thing, we need our X and Y axes labeled. So any suggestions how to do that? Chris, you're on a roll. This is right up your alley. This is the mighty cut and paste world. Add lines. I think you meant get these two guys, right? So let's see how that looks. So we now have our X and Y axes nicely labeled. And our last and hardest step is to get the legend built. So we will go up here and we will copy that legend call right there. And run it. And that's great. It told us what the blue and the red thing are, but we have a couple of more objects on there that we need to deal with. Oh, I hate the editor. So what we're doing here is we're just going to create titles called object 3, 4, 5, and 6, plot it and see what it does, and then we'll figure out how to change the names. Or we could try to read this all ahead of time and do it right the first time, but that's just not productive. Okay, so object 3 is an orange dash line, object 4 is another orange dash line, object 5 is a green dash line, object 6 is a green dash line. That's a huge clue. So object 3 is corresponding to this line, object 4, 5, and 6. So let's just go ahead and grab those right out of the notes. And the last one. Okay, any questions? I mean, that's pretty straightforward. That is cutting and pasting, which is Chris's favorite activity when it comes to programming. So we can cut and paste. Let's go ahead and run it and see what happens. So that's pretty much done. We have completed exercise 1. And if you've been following along and doing it as I did it, you've also completed exercise 1. So give yourself a big yeehaw and let's read on the next exercise in the lab. So lab 2 says a polymer, this stuff, material contains a solvent that dissolves as a function of time. The concentration of the solvent expresses percentage. It's essentially the same problem with a different data set. So if it's the same problem with a different data set, the lazy engineer, which would be all of us, will simply just copy everything and then modify it. So we'll get the data frame in a second. We need the plotting critter. We're going to need that. So we'll copy that. We'll go down to the here and we'll paste it. And we're going to need the ability to initialize and fit a model. So we'll copy that. Paste it, put a space in, put another space in. What else are we going to need? We will need to be able to make a data frame. So copy that. Paste it. And we'll make some name changes. We'll call this one Polymer 2. Why would we want to make name changes? So we can compare later. Good, that's right. And it looks like I've left something out. So I got Polymer 2. Yeah, it looks like I'm missing the initialize and fit data. We would have figured that out on our own, no problem. Let's get those right there. Wonder why that didn't copy and paste. It's a computer, that's why. I think we need model 2 also. Admittedly, not a terribly creative naming scheme, but that'll get us. That's fine. Model 2. Model 2. So we should be able to tell them apart now. And okay, so without changing data, I'm just going to be sure that everything's built correctly. So history 2 looks like history 1. Good. Now all we have to do is change 2 things. Any suggestions? What 2? I'll wait on you to figure out what 2 things we're going to change. In the meantime, let me go ahead and get something built. Demonstrate a rather tricky way to build our data from that. So we copy that and paste it, it does this stuff. However, we can use that if we're clever. So we will wrap that in an outer wrapper, and now we have to simply edit those. So we use the find command. We'll find all the tabs. We'll replace them with a comma. Now we have to put list delimiters on these. And one up here too. Man, all those video games in high school paid off. Let's run that. Make sure that it came out okay. So we're essentially going to use this to build our data frame, but that was a whole lot easier than typing it, and we were able to cut and paste. So now four rows in range length data pairs. We're going to want to do something. We're going to need some place to put data. So we have concentration, data blank, time, data blank. Now, what are we going to do? We're going to append concentration. I spelled that right. Concentration.append. I'm doing this backwards. Data pairs, I'm going to pull the rows out, and concentration is our first axis. Time dot append data pairs, pull the rows out, and we want the second axis. Let's see what happens. Looks like we built it the way we're expecting it. So we will suppress those two, and now we have our new problem. And there is our result. So the last thing our problem says is Compare the results for the data with the example, which is the prior one, and decide which data set produces a better fit and why. So here's the first one. And we can actually use some of the features of our toolkit. I'll just have you look at them. There's the first one. I'm going to just copy it and paste it. Cancel that. That fits a little better. Fits the screen. So using our screen capture capability, I'm going to put the two plots side by side in a second. And we'll get the second one. Essentially is everything's the same, it's just with different data. Let's pull our screen capture. Sizing should have fit better than that, but okay. Would help to put it in the correct lab. And now we'll just display those two closer to one another. So let me think how to do that. I think this will work. Well, not quite side by side, but at least close enough to each other. Model 1, Model 2, Model 1, Model 2. Which one is the better fit? Which one do you think is a better model of the data that's being modeled? Chris G thinks Model 1, Carter Diamond, Model 1. I agree with you. Why are you making that statement? The lines look closer to data points because it's more accurate to our model. Which lines are, okay, the red line is closer to the data points. R squared. Oh, we have a mistake. Let me fix my mistake. There's a reason we did the R squared. Might as well use it. I have the wrong R squared in the plot. I'm not going to recapture the images, but let me get the R squared. Fixed. Okay, so the R squared of our second model is 0.56. The root mean squared error is 12. We go to the Model 1 versus Model 2. This is supposed to be a 0.56, and that's a 12. So our root mean squared error has gone down, but our R squared has also gone down quite a bit. And that is reflecting that these data points are kind of quite a bit more variability as it's moving from left to right versus these ones, which have a very, very consistent downward, visibly linear trend. So your conjecture is mostly right. Accuracy, maybe not the best word choice. The other clue is we look at the left axis. So this one's going from -10 to 60, roughly a range of 70. This one's going from 0 to 60, roughly a range of 60. So they're about the same scale. And given that they're about the same scale, the prediction bands is quite a bit larger in our second model, meaning its ability to predict with any degree of certainty. We have to have a much wider uncertainty band in order to be 95% confident that our prediction is contained between the band. So if these are real data, for instance, you should be very uncomfortable using model 2 unless you have something else to support the modeling effort. Now, let me show you one other useful thing which will help you on some homework that somebody asked. Let's see if I can do this right. I'll just work on the second model. Oh, marker. There we go. Had to get it to join the lines. So I'm trying to get it to join the lines. And this is one of those instances where actually turning the lines on in the plot is helpful for us making decisions. The reason the model isn't quite as awesome is because the data is moving all about. And if we compare that into the prior instance, quite a bit less of moving all about. Now, let me make one more change to illustrate something else. I'm going to take these last two values, cut them out of there, and put them in the front. Take these last two values, which correspond, cut them out of there, cut them out of there, put them in the front. Get rid of that dangling comma, that dangling comma. This is now the same data. There's been no change in data. So it's the same data. Go through that. That old plot looks the same. And it did not do what I expected it to do. Oh, it's because it's sorted. Let's get, this is the plot I guess I'll change. Watch what happens when we join it with lines. It's being really annoying. Notice how when it draws the lines, it starts here, goes to that one, goes back to this one, and then goes through these. That's what's happening to your all's plots in Lab 26, because you were showing them to me and they looked funny. It's funny because your data are not ordered. Your options for ordering data would be to use a sorting approach like it's done here. Or since you have a lot of dots in those things, like 250,000 in each process, just turn off the lines and you'll be able to conclude what you're trying to. All right, any questions on this lab? If you're following along, you're basically done. So I'm going to close that. Let's go look at the homework real quick. So the homework is kind of pretty much the same thing. You have a different collection of data. I just showed you an efficient way to cut and paste that data and then edit it to go ahead and get it into a data frame. And then the rest is literally copy from the lesson or copy from the lab and then interpret the results and answer the questions. So I'll wait about 1 minute. If there are no questions, I am going to shut everything down and wish you all a wonderful weekend. This is an easy laboratory, so don't wait until next Friday to hand it in. Can you show the code that made the graph we made? That one? Get your camera out and take a picture. Oh, I guess it's going on video. So there's nothing magic there. I just, because cut and paste is easier than typing, I just cut and paste and edited out the tabs, put commas in the right place, and just made that into a list of lists, and then slice the list using a for loop. Stuff that you've done by like which we added parts. We added the 2 right here. All we did was just change the names. Model 2. That was me just making sure I didn't clobber existing stuff. Okay. You're satisfied? Excellent. Well, let me go ahead and destroy this copy. That one is unchanged as it should be. Don't need lab 26 after all, because I actually knew what I was doing. That's a first. And I'll see you Monday. I'm not going to be here, so do not come to the classroom Monday. Tell all your teammates that weren't here tonight. Don't bother to go to the classroom Monday because you'll be sitting there alone. There will be a lab on Monday. Josh will lead that and he'll host it. And I'll be back on Wednesday. So Monday, you kind of get a break from me. There's 1, 2, 3, 4, 5 of you. As long as you're not on the same team, I guess the message will get out. Okay, well, I'm going to hang up on you all. Everybody have a great weekend. Bye-bye.